Yes? No? Not really? Yeah. I don't know why I'm right here. Could you guys quiet down? Up front? Could you guys quiet down? Okay. How about, can everybody hear me okay now? All right, cool. Okay, so this is the CS1 Study Union session. Welcome. I passed some surveys around. If you have extras, just like send them towards the back. Those are just like for after, once you're done, just like review the session a little bit. Yeah, okay, let's get started. So how many of you are students with Dr. Mead? And what about with Dr. Zumlansky? Okay, pretty even split. All right, cool. All right, well, so this will be pretty generalized to both of the classes. I'm going to be focusing mostly on material that is new for both classes, and that is most likely to be the majority of your final. Both are technically cumulative, but I saw that Dr. Zumlansky just released the test structure for tomorrow, and it's basically all topics from the new stuff that you guys have been covering. I don't think I have, there's a person back here. Let me go check them. Do I have a, yeah, another mic for, okay.
You just click that one out.
Just click this one. Ooh. All right, let's see. How's this? Much better? Okay, cool. Now I have to put this somewhere, geez. Okay. Okay, so yeah, let's dive into it. The first question that I'm covering is just a basic summation one. So we have a couple formulas that we usually use for summations. And so looking at this one, on this inner part, I'm expecting to use the what's generally written as the sigma from I equals 0 or 1 to n of I, and that gives us n times n plus 1 over 2. And can everybody see that all right? Is that good? Do I need to zoom in more? Or, yeah, a little bit? Okay. This way. Okay. And yeah, basically you just want to break up these summations. So I'm going to solve the innermost one first. And so I'll just separate that. I do j is equal to 1 to n minus 2 of j. And then we just basically just plug into this formula. Our n in this case is n minus 2. So that gives us, we plug in that there, so n minus 2. And then n minus 2 plus 1 gives us n minus 1. And then all over 2. Now this thing right here corresponds to this summation right here. So now we can write it inside the other summation. And we have I is equal to n to 3n of basically this whole thing right here. So n minus 2 times n minus 1 all over 2. Cool. And then from here, I look at this and I see that these n's right here, I is our basically like our looping variable in this case, right? And so the n's are considered constants. And so I can just look at that whole thing and pull it out of the summation, and it'll make it a lot easier to work with. So I just do n minus 2 times n minus 1 all over 2, and then a sum from I is equal to n to 3n. And since I just factored out this whole thing here, I'm just left with a 1, right? And then so this formula right here, we have a formula for summing up a 1 from I equals a to, let's say, n. And that's just n, it's minus a plus 1. And so I'll just use this formula, And so I get this thing still, n minus 2, n minus 1, all over 2. And then this thing, I just plug into this formula up here, and I get, let's see, so, this doc cam is not very good. Here, I had to zoom out just a little bit. Okay. So I plug in 3n for n right here, minus a, which is n, plus 1. And so I can simplify that, or I can just leave it as is. I think on this foundation exam, they just left it as is. Or no, they simplified it, but whatever. That just becomes 2n plus 1. And that's that whole problem. That's all you have to do for that. Does anybody have any questions about that? Just sort of like make a noise or something if you have a question and you're behind me. I don't know why I'm in the center of the room here, but it's kind of annoying. But yeah, any questions about that? Okay, cool. All right, let's move on. Now we're gonna do a quick recurrence relation. So it just says use the iteration technique to solve the following recurrence relation in terms of n. And no, that's just a pretty basic recurrence relation. Give an exact closed form answer in terms of n instead of the big O answer. And then it also tells us that there's a useful formula for this. And so we're probably going to be looking to make something that's in this form right here. So it's just a summation formula. Okay. So what we do when we start out with recurrence relations is we have this base case right here, and we're trying to work towards the base case, but we're going to use iterative substitution in order to work towards that. So looking at this, I have t of n is equal to 3t of n minus 1 plus 1. And so we don't really know what this t of n minus 1 is, and so we need to figure that out. So we just plug n minus 1 into this formula, and we get 3 times t of n minus 2, right, plus 1. And then what we want to do is we want to substitute this thing back in for t of n minus 1 in our original formula. And so we do t of n is equal to 3 times, and then we're going to plug in right here. So we'll do 3t n minus 2 plus 1. And then we need to make sure that we tack on this other plus 1 up here. Everybody with me so far? Cool. Okay. And then, yeah, what's up? Sorry, what'd you say?
Before you close the bracket, you have a 1. Is that from the initial problem? I don't know.
Oh, okay. So the plus 1 inside the parentheses is the one you're talking about? So that one comes from when I figured out what t of n minus 1 is. There's still that plus 1 tacked on because I just plugged in n minus 1 for n into the original formula. Yeah. And so that plus 1 is still there, and we need to carry it over into our iterative substitution. Okay. And then we're kind of left with this t of n minus 2 thing here, and we need to figure out what that's equal to. So we just do t of n minus 2. And it's important when you're doing this, you want to substitute n minus 2 into the original, not the one that you're starting to expand. You want to substitute it into the original formula. And so what we get is just 3t n minus 3 plus 1, right? Because n minus 2 minus 1 is n minus 3. And then we do the same thing. We do t of n is equal to, and so personally when I'm doing these, I tend to leave it in this expanded form and don't simplify just yet. Because the thing that we want to do eventually is we want to see some sort of pattern And it's really, really easy because we're going to see that there's going to be a bunch of 3s, and that tells me, oh, we're looking at powers of 3 right here, right? Or something to do with powers of 3. And so I tend to leave it expanded and then simplify at the end. So we get a 3 times, and then 3 times, and then the t of n minus 2 is 3t n minus 3 plus 1. And then I have to carry this plus 1 here, and then close the parentheses, and then carry this plus 1 here. And yeah, that looks right. Yep, okay. And then so at this point, kind of starting to see a pattern, right? And so I'll simplify from here. And we end up with, usually what I do is I do the inside first. So I'm going to multiply this 3 in, and I'll get 3 times, this gives me 9 right here, t of n minus 3 plus, and then this 3 got distributed onto this 1. And then I have, that 3 gets there, and then I have another plus 1 right here, plus 1. And then I just distribute the next 3, and I get 27t n minus 3. 3 times 3 is 9. Yeah, right there. The 3 gets distributed onto this 3 and gets a 9, and then distributed onto the 1 and it becomes 3, and then another plus 1 right there. So right now, when I look at this, I see, okay, from these 3s right here, I'm getting a nice powers of 3 thing going on right here. So that's one pattern. And then I'm also getting this sum right here, which I don't really want to combine yet, because if I combine those numbers, I would get, what, 13? And it's like, what does that even represent, you know? You can't really see a pattern in that. But if we look at this, it's 1 plus 3 plus 9, which is another powers of 3 thing going on, right? But what are we doing with those powers of 3? We're adding them together, and so we're going to write some form of summation. And it just so happens that if you look, this is a summation where you're increasing the power of each thing that you add on, right? So we kind of found what we're supposed to use there. And so what I want to do is I want to write it in terms of some other variable k, right? And so yeah. And so in terms of k, and I'll write that formula down here once we actually use it, we have 3 to the k, right? T of, and so if we look here, this is 3 to the 3rd power, and that matches up with our 3 right here, right? So we'll have an n minus k. Those are going to be the same number. And then we need to write this as a summation, and it's going to be of this form right here, where our x is just 3 raised to some power, right? And so all I'm going to do is write that as a sum, and I'll have I equal to 0 because we start out with adding a 1, and we want to raise 3 to the 0 power in order to get that. And then I look here, and this is the 2nd power of 3, right? This 9 right here. And so I'm going up to k minus 1 power of 3. And then I'm just going to sum 3 to the ith power. Everybody following me doing that? Good? All right, cool. And so now what we need to do is we need to use our base case. So what we want to do is we want to end up finding this t of 1 is equal to 1 thing, right? And so what we need to do is we need to make this t of n minus k become a t of 1. And so in order to do that, all we have to do is say n minus k is equal to 1, right? And then solve that. And we want this eventually in terms of n. That's what the problem tells us. And so we just need to solve it so that we can substitute into these k's in terms of n. And so all you have to do is like add k to this side and then subtract 1, and we get k is equal to n minus 1, right? And then now we just substitute in for k into here, right? And so we get 3 to the n minus 1 power, t, and then we substitute in here and we get n minus n plus 1 after we distribute this negative sign. And then we add in n minus 1 gives us n minus 2, sum from I is equal to 0 of 3 to the I. And so these n's cancel and we end up with t of 1 here, which given in our base case is just equal to 1. And so we end up with 3 to the n minus 1, and then this becomes 1, so we can kind of just ignore it, plus the sum from I is equal to 0 to n minus 2 of 3 to the I. And then this is a step right here, which I think you can sort of skip, but it makes it a little bit easier to just apply the formula. If you look here, we're saying from I is equal to 0 to n minus 2, and so our last term is going to be n minus 3 to the n minus 2, but then we also just have this 3 to the n minus 1 term here, and so we can just expand our summation a little bit to include that term. And so we can just write this as n minus 1 at the top, and 3 to the I. Did everybody follow what I did there? Okay, cool. And then so the formula that we are given is just sum from I equals 0 to n of x to the I is equal to x to the n plus 1 minus 1 all over x minus 1. And so we just plug into this formula and we get our answer. So we get, let's see, our x here is 3. N plus 1 is just n. So n minus 1 plus 1 is just n. And then we subtract 1. And then x is 3 minus 1 is just 2. And so this is the closed form of this recurrence relation. And so if we were talking about runtime, then this would be a 3 to the n, order 3 to the n algorithm, right? And yeah, that's it. Any questions about that? Yeah, what's up? Here? That one? So this summation is from I equals 0 to n minus 2, right? And so when we expand out these terms, we're going to get 3 to the 0, 3 to the 1, 3 to the 2, all the way up to 3 to the n minus 2. And do you see how we're just adding the next term? If we were to go one further, we would do 3 to the n minus 1. And so I just kind of combine it there. If I didn't do that, I would get a slightly different thing right here, and then I would still have that 3 to the n minus 1 term, and it would still work out to be the same, but it just makes it easier to like simplify it really easily if I combine those. Okay, yeah, what's up?
Where did the n minus k equals 1 come from?
So that comes from the fact that our base case has a 1, right, in the parentheses. So we're trying to find t of 1. And so what we want to do is, since we generalize this right here, we now want to make this thing inside equal to 1. We're kind of trying to see where it converges to, right? And so in order to do that, like, this is probably a little unnecessary. I probably could have just jumped right to it. But when you're doing like logarithmic runtimes and stuff, it's really useful to look at it like this, where you say, okay, my goal is to get this equal to 1. How do I solve this so that it is equal to 1? Any other questions? Right here? Yeah.
Yeah, that one n equals 3.
Okay, yeah.
With the summation, if n is equal to 3, then you have only like 3 to the 1 instead of, and you have a 9 there. Shouldn't it just be n minus 1? So you have 3 to the second power? Is what you're getting is 9? Because then, like, I think it should be n minus 1. Like, why is it minus 2 and not minus 1?
Minus 2.
Because
Oh,
you have 9.
there. That's because we plugged in for k right here with n minus 1. And so this thing was originally n minus 1, and we plugged it in for k, and so there's another minus 1 right there. Do you see that?
Yeah. Yeah. So you wouldn't, for your initial summation, you wouldn't just do n minus 1 plus k minus 1 for the initial one?
Yeah. You want to just substitute directly in for k at each spot. Yeah. Mm-hmm. All right. Anything else? What's up?
I feel a little bit dumb about the 3n, the first 3n minus 1. I know that combines with the n minus 2 summation together.
Uh-huh.
So with n minus 1, 3i, but I'm a little bit unsure as to like how to get there.
How to get there? Yeah, so here, let me expand these terms out. So this summation right here, when we write it out, we get 3 to the 0 plus 3 to the 1 plus 3 to the 2 plus, and then we keep going all the way up to 3 to the n minus 3 plus 3 to the n minus 2, right? And so we have this summation here that equals that. And then we also just have this 3 to the n minus 1 term here, which if I add it on to the end, is still following the pattern, right? And so what I can do is I can just put that into the summation and change my index by 1.
Okay.
Yeah, and so that's what I did there. And yeah, it just made applying the formula a lot easier. All right, anything else? No? All right, cool. Okay, so this next one, it's a little bit different of a question, but so like one thing you're gonna have to do a decent amount is like analyze runtimes of different things and just sort of like step through like how a runtime is derived by just looking at an algorithm, right? And so we have this like pretty useless algorithm right here where we're trying to find the smallest number out of all the numbers that we have in an array, right? And so all we do is we pick a random element from the list, and then we basically hold on to 2 linked lists or 2 lists or whatever. And we say if the element that we're looking at currently is less than the random one we picked, it goes to the left list or list 1. And then if it's greater than, we put it in the right list. And then if the list on the left is empty, then the element that we picked must be the correct minimum value because we didn't find anything less. But if it's not, then we just restart and pick a new random element. So yeah, it's a pretty dumb algorithm, but it's useful to like figure out what the worst and best case runtimes for this are. So when I'm thinking about this, I like How did I go through this one? So, does anybody have any ideas as to how we can figure out the best case runtime for this? So we don't want to think about the best case as the list being empty. We want to assume there's a bunch of stuff in our list and then figure out when it would terminate early, right? But you're right about the worst case being n squared. But do you know what case would cause the runtime to be n squared?
Oh, n squared if it has to run through the first time, if it's all list one and it has to do it again back to the list.
Yeah, it just keeps doing that, right? That would give us an n squared runtime.
That would be order n, because if you just do it once because it list one once, it's still n, and that's it. Done.
Yeah, yeah, okay.
Oh, two.
Yeah, yeah, yeah. Okay, so our best case is going to be order n for this. And then our worst case is going to be order n squared. So basically, for the best case runtime for this, we just assume that our random number generator just picks the minimum element on its own, right? And so, but we don't know that that's the minimum element because we haven't compared it to every other element. So we have to at least do that, right? Because this list isn't in any sorted order or anything like that. And so all that happens to get the best case runtime is the random number generator picks the smallest element. Then every element is put into list 2, right? So every element is greater and it just gets put into list 2. Then we see that list 1 is empty, and then we return the element. And so all we've done to figure out that that's the minimum element is we've compared it to every other element in the list, and then we return it. So we're just doing n operations, where n is the length of the list. And then for our worst case, we kind of just assume that every single time we pick the biggest element, right? And so the key thing here is when we finish and we loop back around to doing the algorithm again, we go back to the first step only using list 1. And so if we assume that we pick like the largest element in the list, what happens is we end up with like a list 1 that's really, really long, and then a list 2 that's just completely empty, right? There's nothing there. And then we have our, what we now found out is the biggest element, right? And then we run it again on list 1. And so the size of our list has gone from n to just n minus 1, right? And if we continue doing that over and over again, we'll have a list of size n, then a list of size n minus 1, n minus 2. And if every time we just pick the biggest element, we're eventually just going to have the summation of runtimes where it ends up being n squared, because it just ends up being this summation right here of I, which gives us the n times n plus 1 over 2. Because our list size just grows smaller, or it shrinks by 1 every single time. Does everybody see that approach, or are people still confused about that? It was like a little bit of a jump. Yeah, what's up? Okay, for the worst case? Okay, so if our random number generator picks the largest element, right, we're going to go through and compare it to everything in this list and end up with a list 1 that's of size n minus 1 because we picked the biggest element, and so everything smaller went to the left list, and then a list 2 that's completely empty, right? And then we restart the algorithm again with just this list right here, And so we end up doing this again, and if we pick the biggest element again, then our list only shrinks by 1 again. And so this becomes an n minus 2, right? And then if we just continue doing that over and over again, we're going to do n operations, then n minus 1 operations, then n minus 2 operations, then n minus 3 operations, all the way down to we just do 1 operation. And if we sum the total time it takes to do all those operations, we end up getting n squared. And it's represented by this summation right here that starts out it adds 1, 2, 3, 4, all the way up to n. Does that make a little more sense? Okay, cool. Any other questions about this one? So yeah, when you're doing this kind of algorithm analysis, you just want to look at one specific step. And if it's the worst case, you want to just assume that everything goes terribly and nothing works out correctly, and just think of the situation in which that might happen, which when you're working with a random number generator, you just assume that the random number generator just does whatever you don't want it to do, right? Okay. Any final questions on this one? Okay. Okay. So now we're going to do some coding stuff. And so this one has to do with binary search trees. And so what it says is write a recursive function that finds the leaf node in a binary search tree, storing the minimum value. So one thing that I thought when I saw this at first, I was like, oh, this is really easy, just the minimum value in a binary search tree. But it's not asking for that. It's asking for the minimum value that's stored specifically in a leaf node, right? And so one of the goals of when we're doing this is that we need to figure out whether or not the thing that we're currently looking at is a leaf node, right? Because that's part of the problem. And then if the pointer passed to the function is null, the function should return null. And then it just gives us a struct and a function definition, and we just got to go at it. So with this one, first of all, we probably want to just handle this case real quick, in case it's an empty tree. So we just say if the root is equal to null, we just want to return null. Right, that one's pretty easy. And so when we're writing recursive stuff, we need to have base cases. And so what would be a good base case to write for this one? So we figured out that our tree isn't empty, and we're looking specifically for leaf nodes. So what could be a good base case? Yeah, what do you think?
If left and right are null, return the pointer to the node.
Okay, yeah, so he said if both the root left and the root right are null, then we just want to return the root, right? So if both the root left and root right are null, then that means we're at a leaf node, right? And so yeah, I think that's a pretty good one. So if we do if root arrow right is equal to null, and root arrow left is equal to null, then we just want to return the root. Okay, so we're doing that now. And now we need to think about how we're going to recursively move through this function, right? So we're looking for leaf nodes, and we're looking for the minimum value stored in a leaf node, right? So with binary search trees, the smaller values are to the left. So we probably want to prioritize moving to the left, right? And then only move to the right if we need to. Because there are cases where, if I have a weird looking tree that's sort of this, right? The minimum leaf node is this one, right? Because that's the only leaf node that we have. And so we need to be able to find that, and so we do have to move right sometimes. Okay. So basically we're going to have one function call, one recursive call where we move left and the other where we move right. Right. And so in what case do I want to move left? Yeah, whenever there is a node that I can move to on the left, I want to go there because that's where the smallest nodes will be, right? So I say if root left is not equal to null. So if there is a left node, we want to move to the left. And we're going to return this, and I'll talk about that in a second. So we'll do return find min leaf, and then we're going to pass it the root left. So the reason we want to return this function call is that once we find the value that we're looking for, we kind of want to pass it all the way back up through our function, right? And so in order to do that, all we do is say, like, once this function exits, which will be when we found what we're looking for, we want to just like continue exiting through the function. And so we want to put the return there. Does that make sense to everybody why we're doing that? Yeah, what's up?
So you return the line
Mm-hmm.
question. So why don't you just, I know because it's a function, you don't set root equal to root left, because let's say you call root left.
Mm-hmm.
What happens if the root left has another value that to its left that's there?
Well, so if the root left has another value, then we'll just continue recursing downwards, right, down the left branch. So we'll go as far left as we possibly can. And whenever we have the option to make a left move, then we will make it, because those values will be guaranteed to be smaller than whatever is in the right. And eventually we'll hit a leaf. Any other questions about that? Okay, so we should only have one more line of code that we need to write, and that's just handling the case where we can't move left, so we're kind of forced to move right until we find a leaf node. And so all we have to do is just after this if statement right here, just do a return find min leaf on root right. And that's it. Does everybody get the process for that one? Yeah. So if we pass null to this somehow, it'll be caught immediately on that, and we won't like dereference anything, so it doesn't matter too much. And by the time we get down here, we've checked to see if the root is null. Then we check to see if its left and right children are null. And then so if it passes this, but then fails this if condition, that must mean that root right is not equal to null. So I could put in here if root right is not equal to null, do that. But because of how our logic is set up right now, it's not necessary. Yeah, what's up?
Since it's a BST, why we still have to go to the right? If like all the value is less than.
Mm-hmm. So the reason that we have to go to the right sometimes is because it's asking for the smallest leaf node specifically. So the smallest node that doesn't have any children. And so in this case, right, this should be the smallest value in our binary search tree, but it's not a leaf node. You see why that is? Yeah, it's because of the problem that we're solving right now. Okay. Any other questions about that? Yeah.
So if we're looking for like kind of like an
Yeah,
Not
yeah,
down for the most part.
yeah. Wherever we, since we chose to move left whenever we could, we instead want to move right whenever we could. Yeah, and then it would, yeah, basically be the same thing except we swap left and right. Yeah. Yeah, what's up?
How it handle
Two leaf nodes? Well, so in what case would we get to two leaf nodes? Yeah. So, with how the BST is, we always want to move left, right? Yeah, yeah, it's a BST. And so, yeah, we'll just choose to move left whenever we can, and so that'll solve any of those. Yeah. Okay. Anything else? Okay, cool. Your time like 7:40. Okay. So now we'll move on to this one. This is a pretty interesting one. It just says write a recursive function that returns the product of the digits of its integer input parameter n. You assume that n is non-negative, and then as an example, so if we were to pass 274 to this, it should return 56 since 2 times 7 times 4 is equal to 56, right? And we're supposed to do this recursively too. Okay. So what would be our base case for this function? Does anybody have any ideas? Yeah, what's up?
If n is less than 10, return n.
Yeah, yeah. If n is less than 10, then we probably want to just return n. And that's because what we're going to be doing is we're kind of going to chop away at this number. And we're going to like multiply the 2 by whatever comes after it. And then the 7 by whatever comes after it. And then the 4 by whatever comes after it. But nothing comes after the 4. And we know that because by the time we pass 4 to this function, it'll be, or whatever the ones digit is, it'll be less than 10. Yeah, and so that's the thinking that we have. And so we just say if n mod 10, or sorry, if n is less than 10, just return n. And then so we only actually need one more line of code in order to finish this function out. And it'll be our other return statement. So we're going to have return. And then we'll probably make a recursive function call. That's a pretty good thing to do, right? And then what are we going to pass to our recursive function call? What'll get us that break that we're looking for? N divided by 10, yeah. We're going to take advantage of integer division here because we're passed in an int. And we're going to do n divided by 10. And so like for 274, when we divide it by 10, it should give us just that 74 chunk. And we'll pass that. And then is that all we need to do, or do we need to do something else? Multiply it by what? The mod. I think it's reversed. Yeah, so we multiply it by n mod 10. Oh, sorry. I had a little bit reversed there. So in this base case right here, in this example, the 2 is what is actually going to be the n in the base case. Because we're going to chop off the 4 and then the 7 and then eventually end up with the 2. Yeah, what's up? Yeah, so that should be fine because the recursive call before you get there, it'll be whatever the ones place digit is, and then you'll just eventually multiply that by 1. So yeah, you technically do one extra recursive call that you don't really need to, but It doesn't really matter in the end, yeah. That's totally fine. Okay. Yeah, and so that's the end of that function. Does anybody have any questions about that? Yeah. Sorry.
So like 274 is and that is 27 or 4.
Yeah, it's specifically yeah, it's a whole number, yeah. Did you have a question? Okay. Go through the logic again? Okay. So basically what we're going to do is we're trying to split up these pieces here. And so in order to do that, if we mod 274 by 10, we end up getting that 4, right? Does that make sense? And so we want to take that and then multiply it by the other digits. And so that's where we get this call right here. But we don't want to include the 4 anymore. And so if we divide that number by 10, we get 27 because of integer division. It chops off that 4 piece, the remainder there. And then so for our base case, all we have to do is just check to see if we only have a number in the ones place and then just return it. And that'll basically we'll do in our first recursive call, we'll multiply 4 by whatever this is. And then our second one, we'll multiply 7 by whatever this is. And then in our third one, we'll hit our base case, return the 2, multiply that by 7, return the 14, then multiply that by 4. Does that make sense to everybody? Any more questions about that? Okay, cool. Okay. So kind of just went from 0 to 100 here, but now we're doing tries, and this will be a recursive function, and we're going to write a function that takes a pointer to the root of a try and then returns the maximum number of words that are prefixes of a single word. And it gives us an example right here where the word intention has 4 of its prefixes as words. So I is a word, in is a word, intent is a word, and intention are all words that are also prefixes of this word, right? And so there's 4, right, in this case. So does everybody have a decent understanding of what a try is, or would you like me to explain them a little bit? Explain them? Okay. So tries are really useful for storing words specifically. So basically in our struct, we have this here, and normally if we were just doing a binary tree, it would have 2 children, right? A left and a right child. Tries generally, when used to store words, they have 26 total children, 1 representing each character of the alphabet, right? And so what we end up having is like, if we want to, let me do it down here. So if we want to store, like, let's say my name, right? What we would do is we would light up this node, which would correspond to the letter M. So basically, like, we do A is 0, B is 1, C is 2, right? And so children index 0 should be the A node, the node that represents A, right? And so basically, we'll light up the M node, and then the A node, and then the R node, and then the T node, and then the Y node, right? And that's not on the screen. Okay. So this is our try. This would be the root right here. And so this is the mth child of the root, and then the A child of this M, and then the R child of the A, right, and so on and so forth. And what we would do to represent that this whole thing is a word is we just put a little 1 in this node, right? And so that says, like, all of these values in these nodes are zeros. And so it says, okay, I'm not done with a word yet, right? And then once we get down to this 1 here, then that says, okay, wherever I've moved so far, that represents a whole word. And so, like, in the case of this word up here, intention, that's a pretty long one. I'll just do intent. So we have I, N, T, E, N, T. Right. So I have this intent word. But so, and I drew this a little small. I is a word, right? So it would have a 1 in its node because I is considered a word. And then in is also considered a word, and so it would also have a 1 in it. And then intent itself is a word, and so it should also have a 1 inside of it. And so this string of nodes right here represents the word I, it represents the word in, and then it also represents the word intent. Is everybody following that description of tries? Seem pretty good? Some, yeah. So a word is technically a prefix of itself. In terms of the problem, that's how they stated it too, and it would be like a little bit tricky, or not super tricky, but just a little bit annoying if they made it so that that wasn't the case. But yeah, so it's mostly in the context of the problem. And this one, like, this one isn't worded super well, I would say. They could have been a little clearer, but you know, that's the kind of thing you should ask about most likely. Okay, yeah, so in the context of this problem, what we're looking for is there are 3 words stored in this word, right? Does everybody see what I mean by that? Like when we get to the very like leaf node of this word, there's 3 total words that we've stored inside of it. And yeah, that's basically the problem. So let's look at how we would code this thing up. So basically, what we want to do is we want to somehow look through our whole try, right? We're going to have to look at everything and then keep track of how many words we've seen when we get down to like a leaf node or the end of a word, right? And so the code for this is like relatively small for what we're doing, but let's just start like simple. One surefire way to start off your recursive functions is to write this base case. So if root is equal to null, we're returning an int from this function, and so we want to return 0. Because we're trying to return the maximum number of prefix words, which is a little bit confusing. But so we don't want a null node to contribute to our total, so we just want to return 0, right? So now we're going to use backtracking in this because we want to traverse our whole try and then just keep track of what we've been doing and keep track of like the solution that we've found so far. And so yeah, this one gets a little complicated. But basically with tries, if you're searching for something, you usually just want to create some for loop that goes through all the children, right? And so we're going to have a for loop that goes up to 26 and it just searches through all the children is what we're going to do. And then so from each point on the try, it'll check all the children and go down every single possible word that you could create or that's represented in that try, right? So we're going to have definitely an int I. And then we probably want to keep track of what our current max is, right? So we could just have, I named it max child, and I'll just set that equal to 0. And then there's one thing they do in the solution for this that's online, and all these are from like foundation exam questions, so like all the typed up solutions are also online. But they call like a max function to figure out like what's the max between the return value and the current max. But like that's technically not defined except in like the math library, so I just use my own, and in order to do that, I need some ret. So, but I'll explain that in a little bit. So yeah, from here I'm just going to do what I said, where I use a for loop to go through all the children. So we'll have for I is equal to 0, I is less than 26, I plus plus. Yeah, what's up?
When it comes to tries, generally, like you were saying, generally the solution is to just go through each character and. Okay.
Yeah. Usually when we're searching for something in a try, or like we're searching for, or we're trying to find the like most represented word, like that's another one. I think that might have been similar to like what was on my CS1 final, was like, oh, find the word that's like most common in this try. And so what you would do is you would just compare the flag values. And so like you can say a word is in a try multiple times by incrementing its flag up above 1, right? So like in this case, if I wanted to say that intent was in the try twice, I would just change this 1 to a 2, right? And yeah, and so in order to search through a try, you just do a for loop that checks all the nodes, because you need to check to see if they're null. And we kind of do that right here. So we're going to make a bunch of like extra recursive calls, but it doesn't really matter in the end, and it cleans up the code a lot if we just do this. Okay. Any other quick questions? Okay. So now what we want to do is we want to make a recursive call on the children, and we want to hold on to the return value of that and then compare it to our current like highest number of prefix words, right? So I'm going to use that ret variable I was talking about, and it's just going to be equal to max num prefix words, and then I'm going to call that on root children of I. So this is like, again, the basic try like traversal for loop. You just have a for loop that goes from 0 to 25, and you call the recursive function on each child in succession, right? And then to figure out whether I've found a number bigger than my previous max, I'm just going to do a little bit of a ternary operator action, and I'll do if ret is greater than the current max child, and then use the ternary operator. So if that's true, I want ret to be the new max child, and if not, I want to keep my current max. And then that's all for that for loop. So basically what it's doing is it's just calling the recursive function on each child, and then receiving the return value from that, and then comparing it to my current max child that I'm keeping track of. And if it's greater, then I just replace it. And if it's not greater, then I still hold on to the max value. Any questions about this? Yeah, what's up? Huh? Oh, that's the ternary operator. So it's kind of like an inline if statement. It's just like It's common in a lot of programming languages, but basically it's saying if ret is greater than max child, sort of return ret. And then if it's not greater than max child, it just returns max child. So in this case, if ret is greater, then max child becomes ret. Otherwise, max child just stays the same. Does that make sense? It's not really something that you need to know for your exam specifically, but it's just a kind of useful thing to keep things small. Okay, cool. Okay, and so we just have one more thing that we need to do. So we've done our iteration and stuff, and now we kind of need to like solve the problem in this step. And so basically all we want to do is once we've like exhausted all of our options, so let's say we're at the bottom of a word, right? Let's say we're down here at the bottom of intent. We check and we run through this for loop and we see that everything's null, right? So that means we're at the bottom of a word. All we want to do is we want to return however many things, or we want to return what's the flag at that node, right? So in this case, we would return 2. But then if we're not at the very bottom node, we want to also add in everything that was below us. So if we're at this node, right, this 2 should get returned up here, and we want to add our 1 to it here, and then add this one to that total, right? Does that make sense to everybody, or do I need to clarify a little? You're like, yeah, what's up? Okay, so basically, once we finish this for loop right here, that means that all our recursive calls have been executed, right? Which means we're ready to return back up to the next recursive call. And the information that we want to send is whatever the current flag is, so like whether or not the node that I'm currently in represents a word, right? Plus however many words were children of the current node. Does that make sense? So like, let's say, I had this as part of my try, right? The word intern. So, wait, that doesn't help. How do I want to explain this? So basically, when I'm at this bottom node, all of my pointers are going to null, right? And so once I figure that out, I want to return the 2 back up so that it can figure out how many total words are contained in its subtries, right? And so I want to return this 2 back up all the way up to here, right? And so when I first return the 2, that recursive call is going to store it in ret, and then if the try is how I drew it out, it's not going to find anything greater than 2, right, in its subtry. And so max child will be set to 2. So like, when we're right here, max child is going to be set to 2. And then when we're here, max child is going to be set to 2 here, and so on. And then once we get to this node, in total, in this like subtry right here, we have 3 words, right? We have in and then 2 occurrences of intent. And so from this node, we want to return 3. And then from this node, we want to return 4. And that'll be our final answer for this try specifically. But so basically what we want to do is we want to take however many words are in the subtry of our current node plus however many words are stored at the current node. Does that make a little bit more sense at least? All right. So basically, it's a pretty simple statement. All we say is just we want to return the max child plus whatever is stored at the current node. So basically all we're returning is whatever is at, however many words are at the current node plus however many words were below it. And so once we return back up and like maybe it goes down another branch, if it finds that there's more words in that branch, it'll replace whatever number was previously there in the max child, and then it'll eventually return all the way back up to the point where we're at the root node, and it'll just return the maximum number. Okay. Yeah, what's up?
Where do you define flag at? Is it
It's in this struct up here, right there. Yeah.
Wait, so is it asking for like intention has 4 prefixes?
Mm-hmm.
Is it asking for 4 or is it asking for like if intent have 2 intents in it, then it would
So
be 5?
if I were to give it this try, it should return 4. And it's the word that, or it's the number of prefixes contained in the word with the most words in it, basically. It's like, yeah, it's a kind of confusing problem. But so basically, it says that the try stores a dictionary of words, right? So we have a bunch of words, and we want to figure out how many words are in the, like, or what's up?
It almost sounds like you're solving for like the count as opposed to. It seems like the question's asking like how many words possible that you have can be this, as opposed to how many words are in the try. Because it's asking for
Yeah.
count.
Okay. I'll get back to it. Here, let me finish. Yeah.
Instead of doing like recursive call, can we just check each node in the try, and then if it flag equals 1, then add some variable counter, and then just return the counter at the end, and that'll give you how many words there are in the total.
Yeah, so that's kind of what we're doing, but what we're trying to figure out, like, we're trying to find a max value specifically, not just how many words are in the try, but if I were to break up a word, what's the most amount that I can break up one specific word?
Right.
Right.
But wouldn't that be just adding all the flags? Like if you just go through and if the flag is greater than or equal to 1,
Yeah.
add 1 to that counter.
So if I were to do that, at this node, my count would be holding on to 3. Because
What I'm saying is like you get a separate variable that just is a counter. Like if it's greater than or equal to 1, then you add 1 to that counter instead of adding 2, which is the value inside of that.
Okay. So we're essentially doing that. Well, so like instead of creating a counter variable that we increment, we instead just use the flag at the current root, which can be used as a counter. I think in this problem they only set it to 0 or 1, but yeah, that's what we're essentially doing with the root flag. Yeah. Okay. Yeah, what's up? So in this example,
of intention should be 4, but having intent to be 3, right?
yeah. And so this is just an example. Like the example that they give here isn't necessarily like what would, like 4 wouldn't necessarily be returned from this function if it was given a dictionary. But if we were to just run this function on a try that contained only the word intention, it should return 4. Does that make a little bit more sense? Yeah. Okay. Yeah, what's up?
It's not already defined in this dictionary, because can you go down and try and say you inserted in before you did intention, then there would be a flag that's saying, okay, there's one count for in.
Mm-hmm.
Then an insertion came in, it would go down the same line, wouldn't it? So you would count, you're just counting up each. Does that make sense? So like if you inserted in and
Mhm.
at n, there was like one count for there. And then you inserted intent, and that means there's one count at in that n, and then there's one at the t.
Mhm.
You're just counting up each one of those.
Yeah, we're basically traversing down each word and counting up however many ones we see, basically, and then figuring out what the maximum number of ones we saw when we went down any one specific word. Yeah. Okay. Any other questions about this one? I'll come back to it later if we have time, but yeah, I have about 50 minutes left, so. All right, I'm gonna move on. Okay, so now we get to some hash stuff. So you learn quadratic, you didn't learn separate chaining, but it'll be really quick, and Zumlansky does cover separate chaining, so we're gonna do it just really quick. Okay. So basically, it's just a pretty simple insert these numbers into this hash table using this hash function. So the hash function is just modding by 12, which is our table size. And to make it easier on us, I already figured out what the mods for each one of these numbers are. So this one is 6, this one's 8, this one's 1, 3, 5, 10, 11, 2, 10, 0. Okay, so those are the numbers I wrote below are just the number modded by 12, which is all our hash function is doing. Okay, and then it just wants us to show if we inserted the numbers in this order from left to right, what would the hash tables look like after we finish inserting, and using different ways of resolving the collisions. Okay. So basically what we do is we take our hash value and then we just insert whatever it corresponds to at that position. So this 234 just goes into position 6. 344 goes into position 8. And so since there aren't any collisions occurring yet, I'm just going to copy them into the other ones because it would be the same way, right? Like they would get inserted exactly the same way since there aren't any collisions. So we do 234 here and 344 here. Okay. So now we insert 481 into position 1. And then 567 into position 3. $893 into 5. $178 into 10. $719 into 11. $686 into 2. Okay, and now finally we get our first bit of action. So we're gonna put in 46 into position 10, right? And so position 10 is already filled, so we have a collision. And so for linear probing, all we do is we just check each cell after, looping back around whenever we need to, right? So we see that there's a collision here, and so we try to put it here. We see that there's another collision here, and so we're at the end of our table, so we loop back around, and we find an empty spot right here, and we just put 46 there. And then I'll just continue with linear probing since we're doing that. Then we insert 84 at position 0. And so with linear probing, we just do this again. We try to put it at 0, it doesn't work. Try to put it at 1, also doesn't work. 2, 3, both don't work, and so we end up putting 84 at position 4. And so that's the final state of the hash table when we do linear probing. Good for everybody? Yeah, what's up?
Do you worry about possibly coding up text, like something with hash tables,
I don't know if he would have you do any coding for it. I know your assignment had to do with hash sets a little bit, but I don't know if he would expect you to code something up with hash sets. It's mostly just knowing how you would use a hash set maybe, and like doing some high level like, oh, this is how I'd use the hash set to accomplish this thing. Or something along these lines where it's like, oh, run through the algorithm of hashing these values into this table. Huh? Yeah, and then doing the different probing techniques, yeah. Okay, any other questions? Or can I move on to quadratic? Okay, so with quadratic probing, we were on 46. So we try to insert 46 into 10, and that doesn't work. So we go to the next cell, and then we see that we can insert it there. And so with quadratic probing, we're going basically to the squares. And so we're going to try to insert 1 position away, then 2 positions away, then 4 positions away, then 9 positions away, and so on, just going up, the squares. And so for this one, we just do 1, 2, 1 and then 2, and we insert 46 here. And then we try to insert 84, and so we can't insert it here, so we do 1. That doesn't work, so we check 2 away. That doesn't work, so we check 4 away, and we just jump straight to here, and we find an open spot, so we insert it there. From the spot that we initially tried to hash to. Yeah. Not from where you last left off, yeah. Yeah, so basically when I'm doing this, I just start wherever I am, I count 1, then I count up to the next square, so 2. Then I count up to the next square, so 3, 4. Then I would count up to the next square, which would be 9, and so I'd go 5, 6, 7, 8, 9, right? One second. It's the next square. What'd you say? Oh, yeah, down here. Yeah, so you loop back around, because we can't put anything down here, so we just loop back around to the top. You start at position 0, but, oh no, you don't change your offset at all. So, like, position 0 right here is 2 steps away from our original hash position. So like from here, I count 1 position down to 11, and then 1 more position up to 0.
Does the pattern stay the same, so the index doesn't matter?
So the pattern changes based on, or the pattern stays the same, but the index that you start at changes.
Right. So
Yeah.
like it doesn't matter where it's full at, you're always going to go 1 and then 2 and then 4.
Yeah, exactly. Yeah. Yeah, what's up? Wait. Did I mess that up? No, wait, I'm pretty sure that I got the right answer. Let me check. Did I mess that up? Oh, oops. Okay, yeah, I messed that up. Sorry about that. Okay. So let's do a little bit of fixing. Okay. Sorry. I had a little bit of a brain fart there. Okay. So when I'm doing 46, I try hashing it to position 10. That doesn't work. And so I go 1 squared away from where I currently am, and I get here, right? And that doesn't work either. And so I go 2 squared away, which is 1, 2, 3, 4, and that doesn't work, right? And so I go 3 squared away, which is 9. So 4, 5, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I mess something else up here? 1, 2, 3, 4, 5, 6, 8. Oh, sorry, I just messed up counting there. Okay, 46 goes here. There we go. Okay, and then 84 goes to position 0, and that's empty. And I just put it there. Okay. So, I messed up a little there. Yeah, what's up?
What's the scale for, it's not 2 to the index, what is the scale for the quadratic?
It's the index, so you're gonna move 0 squared away, then 1 squared away, then 2 squared away, then 3 squared away, yeah. And you just continue moving. So yeah, sorry. I thought 2 was like, I don't even know what I thought 2 was.
You still have to take the mod by the size of it.
Yeah, you're still modding by the table size, but you're doing basically however far away you're going, squared, modded by the table size. Did you have a, okay. Okay, does everybody understand how quadratic probing works? Or, yeah, away. Okay. So let's do separate chaining for those of you in Dr. Zumlansky's class. This isn't something that's covered in Dr. Mead's class, and he's not going to ask about it. Yeah, what's up?
Sorry if you
Yeah.
know this a million times already,
Yeah.
but I just saw, like, you were explaining that you messed up on the 84.
Mhm.
Why is it right there instead of where it was, or why is
Yeah.
46 at 7 originally when it was?
Yeah, so what I messed up doing is I counted 1 away, and then I counted 2 away, but 2 isn't the square of a number, right? I should have counted up to 4 after doing 1.
So you were supposed to start at 10 because 46 is at 10.
Yep.
And you go 1, right?
1. Yep.
And then does that mean it's
And
11
then-
squared,
No,
Oh.
it's 1 squared.
which is just 1?
Yeah,
And
exactly.
you put it there.
So this is the 1 away. That's the 1 squared.
Oh, that's
move.
the 1
Yeah,
squared.
and then I do 2 squared away from the original index. So I do 1, 2, 3, 4, and I check that position, and that doesn't work.
Okay, and then you do, it just goes up 1, 2, 3, 4, 5, all the way
Yeah,
down.
squared, and then
Squared,
that's how
okay.
far away.
Thanks.
Yeah. Okay. Does anybody have any questions about quadratic probing? Okay. So separate chaining is pretty easy. Basically, instead of doing any like weird like index stuff, there's just a linked list at every single node or at every single position in the hash table, and we just do an insertion onto the linked list whenever we try to insert, whenever we get a collision. So all you have to do is just, we hash 46 to position 10, and all we do is we just basically create a linked list here, and then 84 hashes to position 0, and we just put 84 in. And that's all you have to do for separate chaining. Just whenever you try to make an insertion and you find a collision there, you just insert onto its linked list. Yeah. It depends. It's probably, it kind of depends on what you're trying to do. Did he? Okay. On this exam, they did a tail insertion, but they don't really tell you. It shouldn't matter too much, but if it does matter, it'll be stated. Right? Yeah. Like it'll be stated in the problem. We're doing a head insertion to do this. Yeah. Any questions about separate chaining? Okay. So now we're going to move on to heaps. And so basically all this question wants us to do is just show the steps that go into inserting 109 into this max heap. And then at the very end, it wants us to show the array representation of the heap. Okay. So the first step in inserting into a heap is basically what we want to do. We want to find the furthest left position in the bottom row, right? So the furthest left position in the bottom row of this heap is the left child of this 98, and so we just put the 109 there. And then so after we insert into that specific position, we now want to do the percolation or the heapify and like basically fix our heap, right? And so we see that 109 is greater than 98, and so we need to swap those. And so our second step would be to do a 100, and then this side is the same. And then we just swap these two things. So we get a 109 on the right here, and then a 98 on the left. And then we just do the same thing again. We see that 109 is greater than 100, and so we swap it up into the top position. Oops. And then, so this is our final heap. And then when we're trying to represent a heap using an array, basically all we do is we just number the positions starting at the top and working our way down, and from left to right, starting at 0 or 1. So we number this position 1, then 2, then 3, then 4, then 5, then 6, and we can just represent it like this. And that's all we have to do to represent it as a heap. Does that make sense to everybody? You have a question? Yeah. No, you don't need to. So in order for a heap to like satisfy its heap condition, all it needs to have is that the root of any given subtree. Could you guys quiet down a little bit? Sorry, I can't like hear. So the root of any given subtree should be the greatest thing in that subtree, right? And so this 98 and the 60 are in two different subtrees, and so we don't really consider them.
So because the 98 is less than 100, then it's satisfied.
Yeah, it's satisfied, exactly. And so when we're looking at if this 100 satisfies, all we have to do is check its two children, because as long as the children are also satisfied in their subtrees, then the 100 is fine. Does that make sense?
Yeah.
Okay. Any other questions? We're going to do one more heap question, so. Okay. Okay. So in this question, it just says, in her computer science courses, Maria has learned some interesting things about prime numbers and data structures. She has decided to store some prime numbers in a max heap using the tree representation of heaps. If Maria has stored 125 prime numbers, how tall would the heap be? So I don't think this is a question that Dr. Mead would ask specifically, since he hasn't really talked about this formula. But I know Dr. Zumlansky does bring up this formula in class a lot. Basically, the heap is always going to be filled from left to right, and it's going to have the minimum number of rows possible, right? Because we fill it from left to right, top down. And so it's going to be a minimally tall binary tree, and we have a formula to figure out how many levels there are in that tree. Does anybody from Zumlansky's know that? Log base 2 of n. It's specifically the floor log base 2 of n. So our formula is the floor of log base 2 of n. And then there's another way to think about this also. But so basically, if we plug into here, we get floor log base 2 of 125. And that gives us 6. And then the other way to figure this out is basically on the first row of our heap, if we draw it as a tree, there's one total node, right? There's just the root node. And so for level 1, we just take 125 and we subtract 1 out, and we get 124, right? And then for level 2, there's 2 nodes, and so we just subtract 2 out, and we get 122. And then we just continue on until we try to subtract some number that is greater than what our current thing is. And so like 122, the next one, we'll subtract 4 out because there's going to be 4 nodes on that level. And then we subtract 8 out, and we get 110. And let's see, where's my thing? Let me just make sure I'm doing this subtraction right. And then, so we subtract out 16, and we get 94. And then we subtract out 32, and we get 62. And then the next thing that we would subtract out would be 64, which is greater than 62, right? And so this is a level, but it's not a completely full level. And so that's where we stop, basically. And so if we count this up, this represents level 1, right? This represents the second level, third level, fourth level, fifth level, sixth level, and then this is our 7th level, right? And so in that case, since we have 7 total levels, the height of the tree would be 6, right? Because if we're going down 7 levels, we traverse 7 children. Does that make sense? Or 6 children, sorry. Does that make sense? Okay. Any questions about how I worked through that? Okay. Okay, and then so this one just says, here's a max heap, and then clearly draw a circle in the location where the next number will initially be inserted, and then draw a pointer from the parent to indicate which direction it comes off of that parent. And so we kind of did this in the last example. So we're just looking at the leftmost child in the bottom row, which would be the left child of this 1291. Right, so that would be the answer to that question right there. And then it wants us to show each step to inserting 1609. So basically what we do is we do 1447, 81, 1291, 607, 719, and then the left child of this is 1609. And then we need to heapify. And so we swap these two right here. and we get 1447, 881, 1609, 607. And then we just do one more swap right here, and we have 1609 at our root, 881, 1447, 607, 719, and 1291. All right, is everybody good on heap insertions? Any questions about heaps in general? No? Pretty good? Okay. So now, oh, yeah, sure, sorry about that. Yep. How many of you have your exam tomorrow? Okay, a decent amount. There's one section that has it on Friday, so yeah, they're pretty lucky. If you have it on Friday, it's a little late now if you have it tomorrow. Maybe not for Mead section since it's a little later, but look up UCF Foundation exams. They have every single exam since like the 90s posted, and it's all CS1 material for the last like 2 years, and then CS1 and discrete material from then on. And yeah, that's where I pulled all these questions from. All the solutions are also posted online, and that's what like the professors teach towards. They teach you so that you can pass the foundation exam. So definitely work on some of those problems. It's a really useful resource. Okay, are we ready to move on? Okay. Okay, so for this one, it's basically just, yeah, what's up?
Sorry, somebody was asking, will this like PDF the solutions be posted or no?
So I don't have all of them like together in one file because I pulled from a whole bunch of different foundation exams. Yeah, I can probably scan these in. I'll look into that. Yeah, I didn't have time to make one because I also have my own exam. So, but yeah, I'll try to get one posted. If not, you can find all the questions. I think the furthest back foundation exam that I pulled from was fall 2016. So like there's not a ton, yeah. Okay, so using Big O, what is the best case runtime for inserting an integer into an AVL tree that has n integers? So just real quick, with AVL trees, what's our runtimes like? They're logarithmic, yeah. So for this one, it would just be log of n. And then the worst case runtime for inserting an integer would still just be log of n. Oh, and I forgot my Big O. So both of those would just be log of n because it's always maintaining that balanced state. Worst case runtime for insertion into a hash table with n elements, assuming that we use quadratic probing. And then all it says is that we can assume that our hash table satisfies all the conditions necessary to make sure that quadratic probing doesn't get stuck in an infinite loop, which is a possibility. So for this one, basically we can kind of assume, where's that question? So if we're doing quadratic probing on a table that looks like this, right, like this one right here, what's our runtimes probably going to be like if we're trying to insert into that one specific spot? Huh? Yeah, for quadratic probing. Yeah, about order n. And so that'll be the worst case. Because so like one thing that usually happens with hash tables is we'll make sure that our table size is really big, or like at least double however many things we're storing, so that we don't get order n runtimes. But it doesn't specifically say that that condition is being met, and so we shouldn't assume that it is. And so we could get a case where our table only has one spot we could possibly hash to, and we have to go through the whole table in order to find that spot. So yeah, this would be order n. And then, so for this one, given the following hash table, and supposing that no strings have been deleted, but we don't know which order they were inserted, we want to figure out all the possible places where the word of could have been inserted if we use linear probing. So for this one, like obviously of could have hashed to position 4, and so that's one possibility, right? But then, so when we're doing linear probing, we work from the left to the right. And so if of got hashed to 3 here, and Piper was already there, it could have possibly moved over to here, right? And then the same thing with pied right here. And so the indexes that of could have hashed to were 2, 3, and 4. Does everybody see why that's the case? Those are all the possible places it could have hashed to. And it couldn't have hashed to 1, because if it did, then it would have just been inserted into 1, right? Okay. And then using big O notation, what's the worst case runtime for deletion from a min heap that contains n elements? N log n? Why n log n? You don't know? It'll just be log n. So basically, like, we'll delete, and then we'll have to do some percolation or some like heapifying maybe, and we would just like move whatever element got inserted at the top all the way back down to the bottom, which will just be log n, right? So this will be order log n. And then it says draw a min heap that contains exactly 10 elements, and if we were to call the delete min function on it, it would incur that worst case runtime. So the worst possible thing could happen. And so basically the thinking with this, or how I approach this, is I drew my 10 nodes, right? It's the left child right here. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So there's my 10 nodes, and they're going to be linked up like this, obviously. And so if we want to get the worst case runtime possible when we delete from this, we probably want to go to like our node to end up in this area right here. Right, does that make sense? Because that's our furthest. And so what we want to do is we want to create our tree so that the node that we swap up here ends up all the way over here, right? And so like I just kind of started filling in values, 1 here. And then so when we decide where we're going to percolate down, we check the left and right child. And then since this is a min heap, we put the lesser of the two, or we swap with the lesser of the two, right? So at each point, if I want it to go left, I should put the smaller of the two values on the left, right? So I did 10 and 11 right there. And so once I swap up to here, it's guaranteed to swap with 10 because it sees that's the smaller value. And then so it doesn't really matter what I put in here because it's never going to interact with those, so I just put those values. And then from here, I want to do the same thing again. And so I want it to swap left. And so I do 12 and 13 just so that it tends towards the left. And then it doesn't really matter from here which one it goes to because it'll go the worst case either way. And so I just did 17 and 18. And so now we just have to decide what we're going to put in that last node, because that's the one that's going to be swapped with when we do the deletion algorithm, right? We're going to find the furthest right node on the bottom row and swap it and then delete the node down here, right? And so in order for it to go all the way down here, we want this to be a value that's greater than either of these, right? Because we want it to swap with one of those. And so like I just chose 25. It doesn't really matter as long as it's greater than 18. And so when we do deletion from this, we'll swap the one in the 25, the one will be deleted. And then the 25 will swap down this direction, then down this direction again, and then down all the way to the bottom, and that'll be the worst case runtime. Does that make sense to everybody, how I moved through that? I would like very systematically like constructed my heap. Yeah, what's up? It'll eventually end up all the way to the left, but when we do the deletion algorithm, we swap the one in the 25 and then heapify it and restore the heap structure. And so this is a min heap, so we would swap down. Any other questions? Okay. Okay, so a little bit more hash table stuff. So a set of students' names are stored in a hash table implemented as an array of size 25. Their grades out of 100 are used as input into the hashing function. And it just says to suggest a decent hash function to store the names. And then it asks you whether or not your function could cause collisions or clashes and to explain why it might. So a really simple one is to just take the grade and mod it by 25, right? So we're trying to hash grades out of 100 into a table of size 25. And so if we just take the grade and mod by 25, that'll give us our index that we're hashing to. And honestly, you might not, like, there might be better ways to do it, but this is like way simpler, right, than a lot of those. And so, but there are issues with this, and that's that if we do it this way, right, there can be multiple grades that map to the same index, right? So a 0 and a 100 grade would both map to the same index because mod 0, they're both, or mod 25, they're both 0, right? So if two students have the same grade or grade mod 25, so if two students or more than two students have the same grade or their grade mod 25 is equal, then there will be collisions. And so that's basically, yeah, that's the only case where it would be an issue. And then it just says, if the following students have their grades shown and your hash function given in A is used, draw the state of a hash map after the entries are inserted. And then just some stuff about making the picture easier to draw. And so basically, 60 mod 25 is equal to 10. And so I'll just draw my 10 slot right here. And that's where Mary gets put. And then Ben, so 75 mod 25 is equal to 0. And so that gets put in position 0. And then Donna, 13 mod 25 is just equal to 13. And then I'll just say, like, there's positions in between these. Right? And then so that's all that happens, is you just take the grade, you mod it by 25, and that gives you your array index to store the name. Okay. Does that make sense? Is anybody confused by that? So in general, the things that you want from your hash function is you want it to be deterministic, right? So you want it to always map a certain key to the same index every single time. And then you also want it to be well distributed. And so if we assume that the grades are well distributed, then our hash function should be fine because we're just modding each grade, and so the same grade will map to the same spot every time. And if the grades are distributed, then we should get a pretty even distribution in our hash table. Okay. Okay. So we have about 8 minutes left. Does anybody have any like big questions or anything like that that they want clarified about any of the topics? Yeah. What'd you say? It's the amount of time generally. It can be used to represent other things, but generally it's the amount of time given some n input. Yeah. What's up? So with bitmass, basically you can use bitmass in order to isolate a certain bit in a value. So if I were to take if I wanted to isolate the second bit in this, what I would do is I could just do a binary AND with this string, right? And so that, or with that binary mask. And so that will tell me whatever bit is lit up, like whether or not the bit is active at that specific point. And you can expand that to be further too. Mm-hmm. Yeah, you would end up with 0, 0, 1, 0.
What does that tell us, like you have?
It tells you that the second from the right bit is a 1. Yeah. And if the second to the right bit was a 0, then the result from that would also be a 0, because you just zero everything out using that AND. Right. Yeah, what's up? I don't have time to. Yeah. So all like those should be the same tree.
Yeah, I don't know how, but
Okay.
I just don't know.
You can't construct a tree from just an in-order traversal. So as long as you can do it with the other two, you're fine. So like the in-order just gives you the elements in order, but it doesn't show you how they're related to each other. And so you can't construct from just the in-order. Does that make sense? Yeah, like if you were just given the in-order, you couldn't be asked that question.
So if we have a tree in the post order, we automatically get the answer for in order.
Yeah, yeah, because you should be able to construct the tree. Yeah. Yeah.
What was the runtime on question 10 for C?
Which one is that?
10C. I think that was runtime. I couldn't check.
Yeah, it was order N. Yeah. What's your question?
My question was, none of them did x divided by 10 and you modded it.
Uh-huh.
So when I tried to calculate that, I didn't get like the same number. Like, So say you had like 274. So 274 mod divided by 10 is like 27.4.
Here, wait, 1 second. Okay. One last thing, if you could fill out those surveys for me and just like drop them up front here, that'd be like really appreciated. Oh, the group number is 82, I believe. So just bubble 8, then 2. Yeah. Okay. Good luck on everybody's exam. I can answer some final questions if you need me to. Could you